A crate P of mass 1.25 kgs is connected to another crate Q of mass 2 kgs by a light string. The two crates are placed on a rough horizontal surface, so we know that there's some friction there, and then a constant force F of magnitude 7.5 newtons acting at an angle theta to the horizontal is applied on crate Q. Clearly, right? The sketch demonstrates that. And then the crates accelerate at 0.1 meters per second squared to the right, and then crate P experiences a constant frictional force of 1.8, and crate Q experiences a constant frictional force of 2.2 newton. And then the first question, 2.1, state Newton's second law of motion in words, right? I'm definitely not going to do that. And then 2.2, let's draw a labeled free body diagram for crate P, right? So let's pay attention to crate P now. So crate P is connected to crate Q by a string, right? So there must be tension on crate P moving to that direction, right? And then because crate P is lying on a surface, we must have a normal force, right? But then not only a normal force, but even the gravitational force, right? So we should have Fg and the normal force there. And then we are also told that there is frictional force. So let's have a force opposing the motion, right? So let's have F at there. Why is the vector for the frictional force shorter than the vector for the tension, right? It is shorter because the crates are accelerating to the right, right? So the tension, the force of the tension is overpowering that force of due to the friction, right? So we must show that on our length of the vectors. I don't know if I don't know if the examiners are gonna penalize you if your FR is not less than the tension force, but yeah, it's supposed to be less than the tension force because they are moving to the right. We know that they're moving to the right because of that acceleration of 0.1. Anyway, stories 2.1, 2.3, I meant 2.3.1. Let's calculate the magnitude of the tension in the string, right? So we want the magnitude of the tension in the string. In 2.2, we were asked to draw a labeled free body diagram for crate P, right? So let's try finding the tension in the string by using crate P. If we cannot use crate P alone, then we will resort to also using crate Q. So let's try here and see what happens. So we're gonna say for P, right? And we underline it. Why are we doing that, right? It's for the sake of clarity. We're not all over the show. We're showing the examiner that we know exactly what we're talking about. So yeah, let's see what happens. So obviously we have F net equals to MA, being the second law of motion, right? So we start with the bigger force and then we subtract all the opposing smaller forces, right? So here we've already established that the tension is greater than the friction, right? So we must have tension minus all the smaller forces. We only have friction opposing, right? So minus FR being equals to MA, right? We're only considering the forces along the horizontal and not the vertical, right? So when I have tension minus, so the frictional force that acts on crate P is given to us is 1.8. So this will be equals to the mass, which is 1.25 multiplied by the acceleration, which is 0.1. So now the tension is going to be 1.25 multiplied by 0.1 plus 1.8, and that should be equals to 1.925 newtons, right? And just like that, we have the magnitude of the tension. And now let's calculate the magnitude of the angle theta. So the angle theta has to do with our crate Q, right? So now again, Q we underline for the sake of clarity, and we say that F net is equals to MA, right? We leave in the examiner with no doubt. So again, so for crate Q, we're gonna need a free body diagram first before we do this, right? So for crate Q, I'm just gonna draw it here, right? We have the force acting at an angle, right? And then we have the normal, obviously, and then we have Fg, and then we have tension acting and then we also have frictional force, right? So if we compute that, we're gonna have so we on the horizontal axis, né? We're on the horizontal axis. Since it's we're on the horizontal axis, we're gonna resolve F along the horizontal. If we want to resolve F along the horizontal on a flat surface, we say F cos of theta, and then we subtract all the smaller forces. So minus tension minus friction shall be equals to MA. So what is F? We know fully well that F is 7.5, and then cos of theta. What is the tension? The tension, we calculated it in 2.3.1, right? So here we're going to have 1.925, and then for the frictional force is given to us as 2.2. And this will be equal to the mass of 2 kgs multiplied by the acceleration, which is 0.1. So 7.5 cos of theta will be equals to 2 multiplied by 0.1 plus 1.925 plus 2.2, right? We're making cos of theta the subject to the formula. So now it should be easy to see that theta will be equals to cos arc of 2 multiplied by 0.1 plus 1.925 plus 2.2, everything divided by 7.5. Obviously this is more messy, right? It will be more clean if you put this in your calculator first, but yeah, I'm just gonna do what I feel like doing. So theta should be equals to 51.93 degrees, right? And that's how we solve that problem there. Let's look at 2.3. The question says that let's calculate the magnitude of the acceleration of block P while block P is moving on section AB, and the question is for 8 marks, right? It might look intimidating, but it's actually a simple question to answer, right? Let's just address 2.2 first before we can do 2.3. So 2.2 is saying that let's draw a labeled free body diagram for block P, and the question has 4 marks, right? So after solving a couple of problems, well, hundreds of problems under this topic, I realized that if this question has X marks, then the number of forces acting on the object is X. So what am I saying? This question says that let's draw a labeled free body diagram for block P, and then the question is 4 marks, right? So we are expecting to find the 4 forces acting on block P. So if the question was for 5 marks, we would expect 5 forces to be acting on that body, so and so. So if you find yourself in a position where the question has 4 marks and the free body diagram has 3 forces, you're probably doing something wrong. So let's go and look at object P and see what is happening, right? So before we think of anything, we know that there is weight acting on the object, and then it is on an inclined surface. So the inclined surface is going to exert a normal force on the object, right? And then there is a string or a rope pulling it, so we're going to have tension force there, and then we're going to have frictional force, because we can see that our surface is a bit rough. Well, even the question statement says so, right? So what are we saying? We're saying that we have the weight, we have the tension force, we have the normal, which is supposed to be perpendicular to the surface, and then lastly we have the frictional force pulling the object down, right? So just like we were expecting, we have 1, 2, 3, 4 forces, right? If we had anything less, we would assume that we are probably doing something wrong, right? And then the moment you've been waiting for 2.3 says let's calculate the magnitude of the acceleration of block P while block P is moving on section AB, right? So the first step when you want to find the acceleration of a certain object, you draw a leveled free body diagram, right? And then after you do that, you can then say that for the 2 kg object, right? So why am I saying for the 2 kg and underlining it? It's just for the sake of clarity, right? I don't want to make the examiner's life difficult. So after that, you say F net is equals to MA, right? And then you already have a mark before you could do anything else. And then from this step, like I would always say in all the videos, you say the force pulling the object minus all the forces that are opposing, right? I always say that on all the videos. So which force is pulling the object? We can see from the free body diagram that it is being pulled by the tension, right? So we're going to say the tension minus the forces that are opposing. It is easy to see that frictional force is opposing the object, right? The motion of the object up the incline. But then we have weight parallel, which is also opposing. It is not easy to see for most people, but then we have weight parallel, because if we resolve weight, we're going to get weight perpendicular and weight parallel, right? So weight parallel is always down the incline, it's opposing the motion. So we're going to come here and say minus FG parallel, right? Weight parallel or FG, whatever floats your boat, is equals to MA. Our tension, we don't know what our tension is, so we're just going to leave it like that in the meanwhile. And then we have a frictional force of 2.5 Newton. Likely it is given to us, right? So 2.5 and then minus FG parallel. That shouldn't be too difficult. We can calculate that ourselves. We know that it will be the mass, which is 2 kgs, multiplied by gravity, which is 9.8, and then multiplied by sine of 30 degrees, the angle between the horizontal and the inclined surface. And this should be equals to the mass, which is 2 kgs, multiplied by the acceleration, which we do not know. And then if we solve the left hand side, we're going to get the tension minus 12.3 being equals to 2a, right? So we are a bit stuck here. We want the acceleration, we don't have the tension, there isn't anything more we can do. So we're just gonna go ahead and call this equation 1. And then after we do that, we move to the other body. We're expecting that when we move to the other body, whether we're gonna find the tension or we're gonna have two variables again and have to solve simultaneously, right? So let's go to the other object and see what we have. So the 3 kg, right? The 3 kg. Again, we must have a free body diagram before we could do anything, right? The question doesn't ask us to find the free body diagram of 3 kgs, but then it is just good practice so that we can see what is happening before we can answer any question, right? So the free body diagram for the 3 kg, I'm just gonna put it here. Let me just put it here real quick. So we have the weight before we think about anything, right? But with that weight that we're talking about, we know that we have weight parallel, which will oppose the motion. You should always put that in mind, because a lot of people, they sort of leave weight parallel out when they do the calculations because it's not so easy to see. Apart from weight, we have the normal force. And then do we have frictional force? We don't have frictional force on that part of our incline, right? But we have the tension, which is pulling the object down, as we can see. And then we have a force applied at an angle. We have a force applied at an angle, right? But then we cannot use that entire force applied, which is at an angle, right? We would only be interested on the x component of that F applied. Right, so now that we have our free body diagram, we can say that F net is equals to MA. And then the gospel I've been preaching, the force that is pulling minus all the forces that are opposing, right? So I'm going to say Fx minus tension minus weight parallel is equals to MA. So what is Fx? Fx would be 40 cos of 25 degrees. 40 cos of 25 degrees. Minus the tension, which we do not know. And then weight parallel. Weight parallel will be 3 multiplied by 9.8 multiplied by sine of 30 degrees is equals to 3a. Right, so we have that there. Let's go ahead and solve our problem further. So if you solve the left hand side, we're gonna end up with 21.55 minus tension being equals to 3a. You can see that we have something very similar to our equation 1, right? So we're gonna name this equation 2 and solve simultaneously. So the beauty of this kind of equations is that on one equation you have t, on the other equations you have minus t. So if you add equation 1 and 2, t should disappear and you're going to be left with only acceleration, right? So if we add 1 and 2, we're going to get t minus 12.3 plus 21.55 minus t being equals to 2a plus 3a, right? So t plus minus t will be 0, right? And then we're gonna be left with minus 12.3 and then plus 21.55, right? Plus 21.55, and that is giving me 9.25. So I have 9.25, which will apparently be equals to 5a, right? So now it's just a matter of dividing both sides by 5. So if we divide that answer by 5, we get in 1.8 meters per second squared. Right, so that is the magnitude of the acceleration of block P while it is moving on section AB. Right, not too difficult, to be honest. You just need to know a few basics. And then 2.4, if block P has now passed point B. So this is point B here, right? This is point B. So after passing point B, our surface is smooth. There's no friction anymore, right? How will its acceleration compare to that calculated in question 2.3? It will be greater than, right? Greater than. Now, why are we saying so? Let's talk about it. So for block, for the 2 kg block, we had tension minus friction minus weight parallel being equals to mass multiplied by acceleration. So if we make acceleration the same as the formula, you would get tension minus friction minus weight parallel being divided by the mass being equals to the acceleration. So it's easy to see here that if we lose this frictional force, our numerator would have a higher value, right? Meaning that our acceleration will be greater as our F net is now greater, right? We know that acceleration is directly proportional to the F net, so that's why we're saying that the acceleration will actually be greater. This question looks interesting, right? Let's take a look at it and see where we end up. A group of learners design a device that consists of a light bulb on a string hanging from the roof of a cargo truck. This device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down. But when it is undergoing a constant acceleration, the ball hangs down at an angle theta, as shown in the diagram below. And the first question, 2.1, draw a free body diagram of all the forces acting on the ball for 2 marks. So if this question was for 3 marks, you would expect 3 forces on your free body diagram. If it was for 4 marks, you would expect 4 forces acting on your object. And then now that it is for 2 marks, we are only expecting 2 forces to be acting on the ball, right? So let's go ahead and identify those forces. The first force, obviously, it's always weight. Before you start thinking about any other force, you put weight first, and then you go through your situation. Here we also have the tension, the reason why our ball is hanging from the cargo, right? From the roof of the cargo. So to show the tension at an angle, there we have it. We have the tension
and the weight. Why am I choosing to show the tension at an angle? Because in the diagram given, the ball is at an angle 2.2, 2.2.1. In this case, the mass of the ball is 50 grams and the angle theta is 18 degrees. Calculate the horizontal force on the ball. So horizontal force on the ball, the force along the x-axis is what we're looking for, right? Let's resolve that free body diagram first. We have the weight and we have Ty, the y component of the tension, and we have Tx. In this equation, we are looking for Tx, but we don't have the tension. Although we have the angle, we don't have the tension, right? So we cannot calculate Tx directly. What we can do, we can calculate the weight and equate it to Ty. And then after finding Ty, we can then find Tx. So we're going to say that the y component of our tension is equals to the weight. Our object is not moving upwards or downwards, so this equation should be true. So to find the y component of the tension, we're going to say tension, this angle here is 18 degrees. If this angle is 18 degrees, this angle here should be 72 degrees because this angle here is 90 degrees. So we're going to say tension sine of 72 degrees is equals to the weight. Our object weighs 50 grams. So that will be 50 divided by 1000 multiplied by gravity, right? Gravitational acceleration, which is 9.8. It's easy to see now that we're going to divide both sides by sine of 72. So divided by sine of 72, and then we do the same thing on the right hand side. We have to divide by sine of 72. And if you do that, you should get the tension being equals to 0.5152 newtons. So that is the entire tension. We are only interested on the x component. So now we're going to see that Tx is equals to the tension cos of theta. So what is our tension? We know that it is 0.5152 cos of 72 degrees. And if you put that in your calculator, you should get 0.1592 newtons. So there we go. We have the horizontal force acting on the pole. 2.2 magnitude of the acceleration of the track. As soon as I start hearing about acceleration, I'm thinking F net is equals to ma. We want the horizontal acceleration. There's only one force acting on the horizontal, which is Tx. So we're going to have Tx being equals to the mass multiplied by the acceleration. Tx is 0.1592. The mass is 50 divided by 1000 multiplied by the acceleration. So you can see here that we just dividing both sides by 50 divided by 1000, and then we do the same thing on the left hand side, 50 divided by 1000. And if you put that in your calculator, you shall get an acceleration of 3.1842 meters per second squared. 2.3. A and B below are two identical blocks, each with a mass of 5 kgs, joined together by a light inextensible string. The blocks are being pulled with a force of 65 newtons at an angle of 40 degrees to the horizontal, as we can see. The two blocks accelerate to the right at an acceleration of 2.17 meters per second squared, and the tension in the rope is 26 newtons. Right, and then 2.3.1. Let's look at what the question says. Calculate the friction on each block. Let's start with block A. Right, so we don't have the coefficient of friction, so we cannot use Fr is equals to the coefficient multiplied by the normal force. That is not going to work because we don't have the coefficient. What we can do instead is say that F net is equals to ma. So now we put in our tension on block A. So which forces are acting on block A? We have the tension, which is pulling it to the right. And then we have the frictional force, which is opposing. The normal and the weight, which we're not interested in, but anyway, yeah, they are acting on our object. So we're gonna have the tension minus the frictional force being equals to the mass multiplied by the acceleration. The force that is pulling the object minus all the forces that are opposing is equals to ma. So what is the tension? The tension is 26 and then minus frictional force. The mass of the object is 5 kgs and the acceleration is said to be 2.17. So minus frictional force is equals to 5 multiplied by 2.17 minus 26. So the frictional force acting on object A will be equals to 15.15 newtons. Right, that is the frictional force acting on block A. And moving to block B, let's use the same approach. Let's start with the free body diagram. We can never go wrong with the free body diagram. So we have the weight, we have the normal force, we have the tension and the frictional force opposing. And then the force that is pulling, we have Fx, right? The x component of F. And then we have Fy, the y component of F. But we are only interested on the x component of F, right? Again, F net is still equals to ma. What do you do at this step? You say that the force that is pulling the object minus all the force that are opposing. Which force is pulling the object? That is Fx minus all the forces that are opposing. The tension and the frictional force being equals to ma. So to find the Fx, we're going to say 65 multiplied by cos of 40. That is how we find the x component of that force. Minus the tension, which is 26, minus frictional force, which we're interested in, is equals to ma. Our mass is 5 kgs and our acceleration is 2.17. So we're gonna say minus frictional force is equals to 5 multiplied by 2.17 plus 26 minus 65 multiplied by cos of 40. Right? You just put that in your calculator and it is easy to see that the frictional force acting on object B is 12.94 newtons.
The first question, let's draw a labeled free body diagram showing all the forces acting on the block. Labeled free body diagram showing all the forces acting on the block. So let's just go ahead and do that. So the force that we should always start with is the weight. So let's go ahead and do that. So we have weight, right? And then now let's check whether the object is resting on a surface or not. Clearly, the object is on a horizontal surface. So we're going to have a normal force because that surface is going to exert a perpendicular force on the object. And then now, is the surface rough or not? If it is rough, then we are going to indeed have frictional force, right? If you look at the question statement here, we have a block moving at a constant speed over a rough horizontal surface, right? You can see here. So we're going to have frictional force in the opposite direction of the applied force. So we have F here, which is our applied force, right? Frictional force is always parallel to the surface. It's never at an angle, right? And then now the second question, 3.2, pretty much straightforward. Let's state Newton's first law of motion in words. So it says that a body will remain in its state of rest or motion at constant velocity. A body will remain in its state of rest or motion at constant velocity unless a non-zero resultant force acts on it. Now, moving on to 3.3. 3.3 says, let's calculate the magnitude of the force F, right? So we're looking for the magnitude of the force F. So now let's read our question statement so that we can better understand what is going on. So we have a constant force F that pulls a 50 kg block. So we have a mass there of 50 kgs, and then it is pulling it at a constant speed. So what does constant speed tells us? It tells us that the F net is equals to 0. The forces acting on the object are balanced, and then over a rough horizontal surface. So as we already know, we're supposed to have frictional force, and then the coefficient of kinetic friction between the block and the surface is 0.4. So we have a coefficient of kinetic friction which is 0.4, right? So the key takeaway here is that the object is moving at constant speed. So the forces along the x are balanced, just like the forces along the y are balanced, right? So what does that tell us? That tells us that the frictional force is equals to the x component of the applied force. The frictional force is equal to the x component of the applied force, because that applied force, it has a x component and a y component, right? And then we know fully well that we have friction here, right? So the object is moving at constant speed, so the frictional force shall be equals to the x component of the applied force, right? But then what is the frictional force? We know fully well that the frictional force is the coefficient of friction multiplied by the normal force, and that should be equals to the x component of the applied force. We are given the coefficient of friction. It is said to be 0.4, right? And then multiplied by the normal force. Now we just need to determine what the normal force is, and we're going to be able to solve our problem, right? So let me just show you something here on the left hand side. If you have a force that is pointing up, then the normal force is going to be the weight multiplied by the y component of that force, right? And then if you have a force that is pointing down, then the normal force is going to be the weight plus the y component of that force. And then if your force is not an angle and it is just horizontal, then you just have the normal force being equals to the weight, right? So here we have a force that is pointing up, so the normal force is supposed to be the weight minus the y component of our applied force, right? And this will be equals to the x component of the applied force. So we're gonna have 0.4 multiplied by the weight. The weight is mass multiplied by gravity, right? So we're going to have 50 multiplied by 9.8 minus the y component of the applied force. So we're gonna have F sine of theta. But then we know fully well that the angle is 20 degrees. It's given to us, right? So we're gonna have 20 degrees being equals to the x component. So that is F cos of 20 degrees. Now we have 0.4 multiplied by this term, right? If you put that in your calculator, you're gonna get 196, right? And then minus, now we're saying 0.4 multiplied by F sine of 20. So we're gonna have 0.4 multiplied by sine of 20, which will be equals to so we have 0.1368 F. F is an unknown, so we're supposed to leave it like that. And then this will be equals to F multiplied by cos of 20. So what is cos of 20? Cos of 20 is 0.9397 F, right? Because F is a constant. Now let's take this term to the left hand side. The sign is going to change, right? So we're going to have 196 being equals to, so we have 0.9397 plus 0.1368, and that is equals to 1.0765 F. So what do we do now? We divide both sides by the coefficient of F, right? Because we're looking for the value of F. So 196 divided by 1.0765, is equals to 182.07. So that will be 0.7 newtons, right? So the force applied is 182.02. So the force applied is 182.07 newtons. Let's move to 3.4. where we're looking for the normal force, right? So we've already deduced that in this situation, the normal force should be equals to the weight minus the force applied, the y component of the force applied. So what is the weight? The weight is 50 multiplied by 9.8. Now we just need the y component of the force applied. So we're going to have, now we know fully well that the force applied is 182.07, and then the y component, we take sine of the angle, which is 20 degrees, meaning that our normal force is going to be 427.73 newtons, right? And then now on to the last question, 3.5, we're looking for the frictional force, right? The frictional force is equals to the coefficient multiplied by the normal force. The coefficient, we know fully well that it is 0.4. And then we just calculated the normal force not long ago. So now it's just a matter of substituting it here, right? So we're going to have 427.73, which is equals to 171. So we have 171.092 newtons. I've highlighted the important points here. The two crates are lying on a rough inclined plane, and then they're accelerating up the plane with an acceleration of 2.5 meters per second. And then there's a frictional force between the plane and the crate. For the 4 kg crate, the frictional force is 1 newton. And then for the 6 kg crate, the frictional force is 1.5 newtons. And then 2.2 is saying that let's draw a labeled free body diagram for the 6 kg crate. So let's go ahead and do that, right? So before we even think of anything, whether the object is lying on a horizontal surface, inclined or hanging, we're always going to have the weight, right? So we have weight. We must always start with that. And then from there on, is the object lying on a surface or not? Because if it is lying on a surface, then we must have a normal force, right? Let's have a normal force perpendicular to the surface. So there we go, we have a normal force. And then from there on, we can see that we have a force applied. So let's go ahead and have that. And then there's a frictional force of 1.5 newtons. So let's put that there, the frictional force of 1.5 newtons. And then the two blocks are connected by a string. So we must have the tension force somewhere there, right? And then 1, 2, 3, 4, 5. I think we're good to go. So now let's do 2.3, which is saying that let's calculate the magnitude of force F exerted on the 6 kg crate. We know fully well that for the 6 kg block, right? For the 6 kg block, we know fully well that F net is equals to MA. So what do we do from here? Along the forces acting parallel to the surface, we're going to say the biggest force minus all the forces opposing the motion is equals to MA. So what is the force that is pulling our objects? That is F, right? What we're looking for. And then subtract all the forces that are opposing the motion. Frictional force is opposing the motion, and then tension force is opposing the motion with regards to the 6 kg block. And then another force which you might miss is FG parallel, right? Because the weight has a parallel component which is pulling the 6 kg object down. So here we're going to have minus FG parallel being equals to MA, right? So from there on, we're going to have F minus frictional force, which is 1.5 for the 6 kg block, right? And then minus the tension, which seems like we don't know what it is for the moment. So we're just going to have that there. And then minus FG parallel. FG parallel is going to be the mass, which is 6 kgs multiplied by 9.8 sine of the angle, right? Sine of 30
degrees. And then this is equals to MA. M is 6 and then A is 2.5. Right. So now we can go ahead and say that the force minus tension minus 30.9 being equals to 6 multiplied by 2.5, right? So if we make the force the subject of the formula, we're going to get the force being equals to 6 multiplied by 2.5 plus 30.9 plus the tension, right? So now it's easy to see that we don't have the tension. If we had the tension, we would be able to find the force F. So let's go to the 4 kg block and see if we can find the tension. So the 4 kg block, right? So let's draw a free body diagram so that we can see exactly what is happening with regards to the 4 kg block. So it is being pulled by the tension, and then it is being pulled down the incline by the frictional force, and we have the weight, and then lastly we have the normal force, right? So again, if we say F net is equals to MA, we're gonna say that the tension, which is the force pulling the 4 kg block up the incline, minus the frictional force, which is opposing the motion, and FG parallel, that is equals to MA. So from here on, we can say that the tension is equals to MA plus the frictional force plus FG parallel, right? So the tension is going to be equals to, we know the mass, that is 4, and then acceleration 2.5 plus frictional force, which is 1 Newton, and then plus FG parallel. So FG parallel is going to be equals to 4 multiplied by 9.8 multiplied by sine of 30 degrees, right? And then if you put that in a calculator, you will get 30.6 Newton upwards, right, with regards to the 4 kg block. And then now we can substitute this 30.6 Newtons upwards to this equation of F that we had, right? And then we shall be able to find the force therefore. So we're going to have the force being equals to 6 multiplied by 2.5. So 6 multiplied by 2.5 plus 30.9 plus the tension, which we see in it is 30.6. So 30.6, right? And then if you put that in your calculator, we shall get 76.5 Newtons up the incline, right? Up the incline. Right, moving to 2.4. The string joining the crease now snaps while the same force Fx on the 6 kg crate. How will this change affect the following? And then 2.4.1 says the acceleration of the 6 kg crate. Choose from increase, decrease, or remain the same. It is going to increase, right? Let's not forget that for the 6 kg block, we have F minus tension minus frictional force minus FG parallel being equals to MA. So if we make acceleration the subject with the formula here, we're going to get F minus the tension minus frictional force minus FG parallel divided by M being equals to A. So it should be easy to see now that if the string snaps, right, we won't have this minus tension anymore. So our numerator is going to increase, right? And then if the numerator increases and the denominator stays the same, we know that we're going to have a bigger number overall. The acceleration is going to increase. And then now 2.4.2 says that how will the change affect the following: the motion of the 4 kg block. So the motion of the 4 kg block. Let's say at the time the string joining the 2 crease snaps, the 4 kg block has an acceleration of, let's say, v is equals to 50 meters per second, right? So when the string snaps, that velocity is going to start decreasing because the 4 kg block is not being pulled up anymore. So it will decrease, and then at some point of time is going to reach 0, right?
and then after it reaches 0, it's going to stop and then start sliding down.
A block of mass 24 kg is on a rough horizontal table. As soon as I read rough horizontal table, I know that there's some frictional force acting on the block, right? And then it goes on to say a force F is applied to the 24 kg block at an angle of 35 degrees to the horizontal. The 24 kg block experiences a force of friction of 7 Newton as it moves. We are even given the frictional force, right? It goes on to say that the block is connected by a light inextensible rope which passes over a light frictionless pulley to another block of mass 12 kg, clearly indicated on the sketch, which hangs vertically as shown in the diagram below. And we are told to ignore the effects of air friction, as we always do. And then it goes on to say that the 24 kg block moves to the left at a constant velocity. So the 24 kg block is moving to the left. Let's just indicate that. And then now 2.1 says state Newton's second law of motion. We know that F net is equals to ma, and if we make a the subject of the formula, we get a is equals to F net divided by m. So clearly here, if you apply F net on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the applied force and inversely proportional to the mass of an object, clearly. And then you can also say that F net is equals to delta P divided by delta T. That is Newton's second law in terms of momentum. And it will say that the net force acting on an object is equal to the rate of change of momentum of the object. And then now we can move to 2.2. 2.2 says, what is the resultant force acting on the system? If you pay attention to this statement here, it says that the 24 kg block moves to the left at constant velocity. Constant velocity implies that our acceleration is equals to 0. If acceleration is equals to 0 and F net is equals to ma, then F net is equals to 0 newtons. So 2.2, we have 0 Newton. And then now we can move to 2.3. 2.3 says, draw a fully labeled free body diagram to all the horizontal forces acting on the 24 kg body, right? So that's our free body diagram there. And then we have the tension as a consequence of the string attached to the 20 kg block, right? And then we also have friction that is going to the right because our object is said to be moving to the left, right? And then our force applied is supposed to be moving to the left, right? So we have force applied here. I'm trying to make the error of the force applied to be equals to the tension plus the friction, right? Because these forces are balancing out. As a consequence, our object is moving at constant velocity or with an acceleration of 0. So now we can go to 2.4. Before we go to 2.4, if you want to support the channel, please check the link on the description there. And then 2.4 is saying calculate the tension in the rope, right? For our 24 kg block, we don't know what the tension is. We know what the friction is, but we also don't know what the force applied is, right? But for our 12 kg block, let's have a free body diagram for our 12 kg block. We have the tension that is pushing up, and then we have the weight that is pushing down, right? And then we know the weight, obviously, because we have the mass. The only unknown variable is the tension. So here, clearly, it will be easier for us to use the 12 kg block to find the tension versus the 24 kg block, right? Because on the 24 kg block, at this point, we have two unknown variables. So for the 2 kg block, so I'm writing 2 kg, we have F net equals to the mass multiplied by the acceleration. So it's just two forces, the weight minus the tension is equals to MA. These two forces are said to be equal, right? So the order really doesn't matter, but usually I start with the bigger force and subtract all the other forces. So what is the weight? The weight is 12 minus 9.8 minus tension being equals to this is 12 kg, not 2, being equals to 12 multiplied by 0, because we know that it's moving at a constant velocity. So we're gonna have minus tension being equals to minus, let me just put that in my calculator real quick. I don't want to embarrass myself, right? So we have 12 multiplied by 9.8, that is 117.6. So our tension is basically 117.6 newtons. It says let's calculate the tension, right? So we can put a direction here. So for the 12 kg block, it will be to the left, right? And then for the 24 kg block, it will be to the right. Yeah. So let's do 2.5. 2.5 says let's calculate the magnitude of force F. So now if we come back to our free body diagram for the 24 kg block, now this unknown variable of tension, we now have it, right? So we have tension, we have friction, we just need FA. So again, we're gonna say 24 kg, and then we have F net equals to MA, and then force applied, we're saying that it's supposed to be equal to the tension plus the friction, right? So it's bigger than those individual forces. So we're gonna have F applied cos of 35 plus minus tension minus friction is equals to MA. Now let's talk about this cos 35. So the force applied is at an angle of 35 degrees to the horizontal, right? We want to resolve it to the x along the x-axis. On a flat surface we use cos, and then on an incline we use sine. Clearly we on a flat surface here, so that's why we say in FA cos of 35. So it will be FA cos of 35 minus 117.6 our tension, and then minus 7 is equals to 24 multiplied by 0. Why am I saying minus 7? Look here, we are told that the frictional force is 7 Newton, right? So from here, what are we gonna have? We're gonna have FA cos of 35 equals to 24 multiplied by 0 is 0, right? And then we take in minus 117.6 and minus 7 to the right hand side. We're gonna get 124.6. We divide both sides by cos of 35. So 124.6 divided by cos of 35. So I'm getting a force applied here of 146.1343 newtons to the left. We are only actually it's not to the left, it's at an angle of 35 degrees, right? Yeah. Plus even the question only needs us to find the magnitude of force F. So 2.6 says force F is now removed. Does the magnitude of the normal force increase, decrease, or remain the same? So let's find
formula for the normal force so that we can see what happens. So here on our object, when we're talking about the normal force, we now pay attention to the forces acting on the vertical, right? The normal force is pointing up, obviously, and then we have the weight going down, and we have F applied to the Y, right? So clearly from these forces, the normal force is supposed to be equal to the weight plus FAY. So if you remove this force, the normal force goes down. Clearly, the normal force will go down. So here we're gonna have decrease. So let me show you something. It will not always go down when you remove a force. Let's say this force, the force applied was acting up, right? Then we were gonna have the normal force, and then F applied Y, and then down we still have weight. So from this sketch here, we're gonna have the normal plus FAY equals to the weight. So the normal is equals to the weight minus FAY. Clearly in this case, if you remove FAY, the normal would go up. I think I've defined Newton's second law of motion more than 100 times. So for this video, let me just skip it. Only these ones. Let's start with 2.2.1. The coefficient of kinetic friction between the slope BC and the block M2 is 0.2. Draw a labeled free body diagram for block M2. Let's go ahead and take a look at block M2 and see what we can do. So before we start thinking of anything else, we need to indicate the weight first. After indicating the weight, we can then look at the other forces. Our object is resting on a surface, so we expect a normal force. M1 and M2 are connected by a light inextensible string, so we are going to have our tension force. The mass of M2 is 70 kgs. The mass of M1 is 12 kgs. So it would make sense to assume that M2 is moving down the slope. If that is the case, then the frictional force will be up the slope. 2.2.1, it is for 4 marks, and we have 4 forces on our free body diagram. So we are quite confident that we have not missed anything. Let's go ahead and do 2.2.2. Calculate the magnitude of the acceleration of the system. Show all steps in your calculation. Well, let's start with M2 because we already have a free body diagram. So this is for M2. Why am I writing M2? I want to show the person that is marking my script exactly what I'm talking about. Yeah, I don't want any confusion whatsoever. So F net is equals to MA. This is how we always start. What do we say now? We say the force pulling the object minus all the forces that are opposing. M2 is sliding down the slope. That is due to the parallel component of the weight. So we have FG parallel minus the frictional force minus the tension force being equals to MA. So how do we calculate FG parallel? That is mg sine of theta. So we're going to have 17 multiplied by 9.8 multiplied by sine of 30 degrees minus the frictional force. The frictional force, that is the coefficient multiplied by the normal force. Our coefficient is 0.2. The normal force is mg cos of theta. So that will be 70 multiplied by 9.8 multiplied by cos of 30 minus the tension being equals to 70 multiplied by 8. We're going to have 224.1813 minus the tension force being equals to 78. As you can see, we have 2 variables but 1 equation. We need 2 equations. Let's name this equation 1 and set up our equation 2. We're going to find equation 2 using M1. Let's draw a free body diagram for M1. We have the weight, obviously. We have the tension, which is pulling it up the incline.
we have the normal force. M1 is experiencing no frictional force, so we can leave it like that. When we set up our equation, the force that is pulling M1 is the tension minus the force that is opposing, the parallel component of the weight. So we have Fg parallel being equals to Ma. We're going to have the tension minus Fg parallel. The mass is 12 multiplied by 9,8 multiplied by sine of theta. The angle of inclination is 50 degrees. So we're going to have sine of 50 being equals to 12A. So we're going to have the tension minus 90.0868 being equals to 12A. This is our equation 2. Let's add the two equations. We're going to add the left-hand sides together and the right-hand sides together. Minus tension and plus tension will cancel out. We're going to be left with 224.1813 minus 90.0868 being equals to 82A. This is just 134.0945 being equals to 82A. We need to divide both sides by 82, obviously. And if we do that, we're going to get an acceleration that is equals to 1.64 meters per second squared. We are only interested on the magnitude. We don't need to indicate the direction. 2.2.2, let's do 2.3. So 2.3 is saying that if the angle of slope BC is decreased to 20 degrees, initially it is 30 degrees and now it is being decreased to 20 degrees. Will the frictional force between the block and the slope increase, decrease, or remain the same? Explain your answer. So the frictional force is going to increase. Let me show you why. The frictional force is equals to the coefficient multiplied by the normal force. The coefficient, it depends on the material. So whether we increase or decrease the angle, the coefficient is not affected. So now we are only looking at the normal force. Well, the normal force is equals to mass, gravity, and cos of theta. Well, the mass is constant and the acceleration is also constant. So we are just looking at cos of theta. If the angle decreases, does the normal force increase or decrease? We know that cos of 0 is 1 and cos of 90 is 0. If you decrease the angle, the normal force increases. If you increase the normal force, the frictional force is going to increase.
I'm going to post other questions from this question paper. So make sure you subscribe so that you don't miss any of that. So let's look at the question we have here. It says an 8 kg block on a rough horizontal surface connected to a 2 kg block by a light inextensible string passing over a frictionless pulley as shown below. The 8 kg block moves at a constant speed. So when we hear constant speed, we know that the acceleration is equals to 0 meter per second squared, right? So this implies that the F net acting is equals to 0. And then it goes on to say when pulled by a 29.6 Newton horizontal force to the right, the frictional force acting on the 8 kg block is 10 Newton. There we have it. The first question says state Newton's second law in terms of motion. Assuming that you already know what that is, so I'm just going to move on. We have 2.2. 2.2 says draw a labeled free body diagram for the 8 kg block. So if you have went through questions like this, I'd advise you to pause and then do the equation by yourself, and then you then watch me do it. So the free body diagram on the 8 kg block. Okay, there we have the 8 kg block. It's lying on the horizontal surface. Because it's lying on a surface, the surface is exerting a normal force upright. Yeah, so there we have it. And then gravitational force is always acting. Yeah, so we're gonna have Fg or W for weight, whatever you wanna call it. And then we have our force that is being applied there of 29.6 Newton. So I'm gonna put that there, and then they say that friction is acting, so we're gonna have Fr, and then it is also it's connected to a 2 kg block through a string, so we have tension, right? So I'm just gonna put it there. So yeah, there we have it. Those are the forces acting on the 8 kg block. The tension and the frictional is equals to the F that is being applied, right? And thus it is moving at a constant speed, like they stated. So let's carry on. Let's move ahead. Says 2.3, calculate the tension in the string. So let's look at the 8 kg block. So let's say 8 kg block. I'm not choosing 8 kg, the 8 kg block, because it's the one I like the most. 8 is not my favorite number. I'm choosing it. I'm just trying it out. I will write all the given information for the 8 kg block and then see if I get to the answer. If I don't get to the answer, I'll then use the 2 kg block. So I'm not choosing the 8 kg block because I like it so much. But then usually in questions like this, if you have a 2.1, the answer for 2.1 helps you answer 2.2, and the one from 2.2 helps you answer 2.3. So because 2.2 says the free body diagram of the 8 kg block, it's most likely that 2.3 you will be using the 8 kg block. But then let's just go ahead and see. So the law we're sticking to is Newton's second law of motion, obviously. So we're gonna have F net, F net equals to mass multiplied by acceleration, and then we also know that F net is equals to the first force, the second force, and then some force n, right? So what are the forces acting on the horizontal on the 8 kg block? We know that from 2.2 we have the force applied, we have the tension, and then we have the friction. So if we write that down, we're going to have this force which is being applied plus the tension force plus the frictional force equals to 8 kg multiplied by 0, right? Because that is we have an acceleration of 0 because it is moving at constant speed. So what is F? F is given to us is 29.6. What is T? T is our variable of interest. So there we have T there, and then plus friction, right? Friction opposes the motion. It's opposing the motion like the tension. So we're going to put a negative value there. It says that the frictional force is 10 Newton. So we're going to have minus 10 equals to 0, right? So 29.6 minus 10, that is 19.6. So we're going to have 19.6 plus T equals to 0. Take 19.6 to the other side, you get T equals to minus 19.6 Newton, which makes sense because T is opposing the motion, so it's supposed to have a negative value. So let's move ahead. For 2.4, they say that the force we have is now increased to 15 Newton, right? So we're going to have F equals to 15 Newton, and then there we have it. And 2.4.1, 2.4 says apply Newton's second law to each block and calculate them. 2.4.1 then says magnitude of the acceleration of the 8 kg block. Okay, so let's start with the 8 kg block and see if we can get the acceleration using the 8 kg block only. And then if we cannot, then we'll then involve the 2 kg block. But then let's start with the 8 kg block. So the 8 kg block, we're sticking to the basics. We know that F net equals to MA. This is equals to the sum of all the forces acting on the object. So from F1 to some Fn, n being any number of the forces we have. So F1, the force being applied, 15 Newton. There we have it. And then we have tension opposing. So we have minus t, and then we have the frictional force, which is said to be 10 Newton, right? So that is minus 10, and then equals to 8 multiplied by acceleration, right? And then okay, and then this will be our equation 1, because now we have 2 variables, right? So we need another equation. If you have 3 variables, you make sure you get 3 equations. If you have 4, you get 4 equations, and then you can solve. So another equation, we'll get it by using the 2 kg block. The question sort of gives it away because it says apply Newton's second law to each block. But then even if it doesn't say that, if you're trying to find acceleration and tension, and then you find yourself in a situation where you have 2 variables, you have to use the other mass or the other block, the other whatsoever, to find the second equation, and then you can solve simultaneously. So let's go ahead for the 2 kg block. For the 2 kg block, there's 2 forces acting at the tension and gravity. So we're gonna have the tension minus gravity, which is equals to ma, right? The mass is 2 kg, so let me just go ahead and put 2, and then that's been multiplied by a, which we don't know what it is, and then our t equals to minus fg is the mass multiplied by 9.8, right? So there we have it. This is equals to 2a, so we're gonna have t minus 19.6 equals to 2a. This is our equation 2. Some people like complicating their lives. They want to solve this simultaneously by making t the subject of the formula and then substitute on the other equation. But then the way I like doing it is like on the first equation, look at this part. We have minus t, right? And then on the second equation, we have t. So if you add these 2 equations, t is gonna disappear, and then you're gonna actually it's not going to disappear. That's technically wrong. They're going to cancel out, so you're gonna be left with only a, and then you can just solve for acceleration. So let me practice what I preach. So equation 2 plus equation 1 will give you, so I'm adding 2 to 1, so I'm gonna have 50 minus t minus 10 plus okay, let me, yeah, and then t minus 19.6, and then that's it, equals to 8a plus 2a. This is equation 1, and then I'm adding equation 2. Okay, so t and t are going to cancel out, like you see. So here on this side, I'm gonna be left with 50 minus 10 minus 19.6 equals to 10a. This implies that a equals to 50 minus 10 minus 19.6 divided by 10. Let me put that into my calculator real quick. So 50 minus 10 will give you 40 minus 9.6 minus 19.6 divided by 10, and then I'm getting an acceleration of 2.04 meters per second squared. Yeah, so there you have it. That's how you solve this problem. Let's carry on. Last but not least, 2.4.2 says calculate the tension in the string. We have this equation 1 here. There you have it, and then we have this equation 2 here, and then we're supposed to find acceleration. So we can just sub in the t we found on 2.4.1 in any of these equations. The second equations looks a bit simple. It's easy on the eye. It doesn't look as complicated as the first one. So let's sub t on the second equation. So we have t minus 19.6 equals to 2a. So t equals to 2 we're saying that A is 2.04, right? And then we add 19.6. Let me put that in my calculator real quick. 2 multiplied by 2.04 plus 19.6. That gives me 23.68 Newton. And that's it for this problem. We're done with it. Make sure you subscribe. I'm going to post other questions from this question paper, the May June from 2021. This question is saying, let's calculate the maximum height above the ground reached by block A. It sounds like a typical vertical projectile motion, but it is way more than that. You're gonna see what I'm talking about when I answer the question. Can I even answer the question? That's the question on its own. Let's do 2.1 so that I can show you what I'm talking about. So 2.1, the question is saying that let's show by means of calculation that the magnitude of the acceleration of block B was 3.88 meters per second squared while the block was moving vertically downwards. So let's go ahead and read our question statement so that we can see what is going on. So when block B is released, so now we know fully well that this block B is released at some point. It moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. So if it is released, then we know that VI is equals to 0 meters per second. And we're given VF, the velocity at which it strikes the ground. It is said to be 3.41 meters per second. What else do we have? We have the distance or the displacement of our object B, right? From the time it is released to the time it strikes the ground. So we have delta Y being equals to 1.5 meters. And what are we looking for? We're looking for the acceleration, right? So based on the vertical projectile motion, you can see what we have to use here. VF squared is equals to VI squared plus 2a delta y. We have VF squared, we have VI, we have delta y. So we can use this formula for sure, right? It's gonna work because we're looking for the acceleration. So let's take direction towards the ground as positive. If we do that, then our VF is 3.41 squared, which is equals to our VI, which is 0, we square that, plus 2a, and then if we take in direction towards the ground is positive, then our delta y will be positive 1.5. We're gonna have 11.6281 being equals to 0 squared is just 0, right? And then here we have 2 multiplied by a multiplied by 1.5. That is equals to 3a. So if we divide both sides by 3 in order to find our acceleration is equals to 3.88 meters per second squared, right? And that's exactly what we are asked to prove. So our answer for 2.1, we're quite confident we're doing the right thing. And then now 2.2, let's draw a free body diagram showing all forces acting on block B immediately after it was released. Right, so let's just go ahead and do that. So for block B, we're gonna have the weight pointing downwards, right? And then now we can start thinking about everything else. You know the weight is gonna be there, so you put the weight first, and then after that you have to start thinking about everything else, right? It is connected to a light inextensible rope, so we're supposed to have tension force going up, right? So we have tension and weight. We have two forces acting on the object, and the question also has 2 marks, right? So we're quite confident we were able to identify all the forces. If the question was out of 3 marks and we had only 2 forces, we were most likely going to be doing something wrong, right? You should be aware of that. And then 2.3, this is the one I want you guys to do. State Newton's second law of motion in words, right? We know that the acceleration directly proportional to the F-net, and so on and so on. Let's just do 2.4, right, before doing 2.5. So 2.4 is quite an interesting one also. It's saying that let's calculate the value of M by applying Newton's second law to each block while they are in motion. People are getting this question wrong so often, such that they're telling you to apply Newton's second law in each block, right? They usually just say calculate the value of M, and you have to figure it out yourself that you have to use Newton's second law on both blocks. But then now they're actually telling you, let's go ahead and apply it on block B and see what's going to happen. So for block B, we have the free body diagram, right? So we're going to say F-net is equals to MA, and then we're gonna say the force that is pulling the object minus the force that is opposing. The object is going down, right? So it means that we have the weight pulling our object, and then the tension is opposing. So we're gonna say that the weight minus the tension is equals to MA. So what is the weight? The weight is 7.5 multiplied by 9,8. Minus tension is equal to the mass, which is 7.5 multiplied by our acceleration, which is 3.88. So what is 7.5 multiplied by 9.8? That is 73.5. And then minus tension is equal to 7.5 multiplied by 3.88. Which is equals to 29.1. So minus tension will be equals to, so now we take in this term here to the right hand side, so that it will be 29.1 minus 73.5, which is equals to minus 44.4, right? So if we divide both sides by minus 1, we're gonna get the tension being equals to 44.4 newtons. Right, we have the tension, but that's not what we're looking for. We're looking for the value of M, right? So now we have to go to that object. So for object A, still F-net is equals to MA, right? There's no other way. So let's have a free body diagram for object A so that we can see what is going on. So for object A, the tension is pulling the object upwards, right? And the weight is opposing. So here we must have tension minus the weight, because now it is the tension that is pulling and the weight that is opposing, unlike in object A. Right, so the tension, we know that it is 44.4 minus the weight. The weight should be M multiplied by 9.8 is equals to the mass multiplied by the acceleration, which is 3.88. Right, so we're gonna have 44.4 minus 9.8 M is equals to 3.88 M. It's easy to see that we're gonna have 44.4 and then it's equals to, so we take in this term to the right hand side, so that is 3.88 plus 9.8, which is equals to 13.68 M. If we divide both sides by 13.68, we're gonna have 44.4 divided by 13.68, and then the size of our mass is 3.25 kgs, right? So we have our mass, the value of M, that is 2.4. and now 2.5, let's just do 2.5 real quick. So let me show you something. Let's calculate the maximum height above the ground reached by M. So initially I was thinking, why does this question have 5 marks? It should have 1, because from this point here to the ground it's 1.5, and then while B is moving from that height to the ground, then A will move from the ground to that height, which is 1.5. So the maximum height for A should be 1.5. Why does it have 5 marks? I don't understand. But then I realized that when it reaches this height, which is 1.5, it has a velocity which is not equals to 0, right? So it's still going to go up for some time because its velocity there is not 0. So it's not stopping. It's still going up until it ultimately gets stopped by gravity. Right. So what is the velocity at this point? That is the question we are interested in. The velocity at that point is equal to the velocity that the object B strikes the ground with. Right. And then what is the value of that velocity? That is 3.41. It is given to us here. So at this point here, at this height, ball A has a velocity of 3.41 meters per second. I was not so sure about the velocity of A at that point. I actually calculated it. And then I realized that, okay, fine. The velocity at which ball B strikes the ground with is the velocity of ball A at that height, because the acceleration is the same, and then VF is not dependent on the mass. When we're using VF squared, it's equals to VI squared plus 2A delta Y. So we have the velocity at that point. We want the maximum height above the ground, right? But then another thing we have is VF, right? Which is at the maximum height we're interested in. That VF is equals to 0. Because at that point, your object will no longer be going up. So if we find this height here, and then we add it to the 1.5 we have, then we have the height of object A above the ground. So let's go ahead and do that. We're saying that VI will be close to 3.41 meters per second, and VF will be equals to 0. Right. Our acceleration, how much will our acceleration be? If we take upwards is positive, our acceleration will be minus 9.8 meters per second. That is because when ball B strikes the ground, object A will now be in free fall. The tension force on that rope is going to be equals to 0. Right. So we have VI, we have VF, we have the acceleration, we want delta Y. Right. So it's easy to see now that we can say that VF squared is equals to VI squared plus 2A delta Y. So VF is 0, maximum height. And then VI, if we take it up as positive, that is 3.41 squared plus 2 acceleration minus 9.8 because we're taking upward as positive, and then multiply by delta Y. So we have to take this term to the left hand side. So 3.41 squared is equals to, so 3.41 squared is equals to 11.6281, right? If we take it to the other side, we're gonna have minus 11.6281 being equals to 2 multiplied by minus 9.8, that is minus 19.6 delta Y. If we divide both sides by minus 19.6, we're gonna get 0.59. So 0.59 meters is equals to delta Y. So here we have 1.5, and then here we have 0.59. So our height above ground, is 1.5 plus 0.59. Right, that will be our height. That is equals to 2.09 meters. So we have two blocks here, one of mass 2 kg and the other one of mass 5 kg. And then there's a force applied on the 5 kg block at an angle of 20 degrees. And then we are told that the 2 kg and the 5 kg blocks, they both experience kinetic frictional forces, right, of 10 Newton and 15 Newton respectively, right? So the 2 kg block experiences a kinetic frictional force of 10 newtons, and then the 5 kg a kinetic frictional force of 15 Newton. That's what respectively is basically telling us. And then the first question, 2.1.1, it says, let's state Newton's second law of motion. Again, Newton's second law of motion in words, it just states that when a non-zero resultant force is applied on an object, the object will accelerate in the direction of the non-zero resultant force with an acceleration directly proportional to the F net and inversely proportional to the mass, right? So we know fully well that F net is equals to ma, and then in this equation, if you make acceleration the subject of the formula, you basically get the definition, right? Acceleration will be equals to F net divided by the mass. Clearly in this case, the acceleration is directly proportional to the F net and inversely proportional to the mass, right? And then 2.1.2 says, let's draw a labeled free body diagram for the 5 kg block. So here's our 5 kg block here, right? So free body diagram, we denote the body with a dot, right? So there we have our dot. We are told that there's a force applied, right, at an angle of 20 degrees relative to the horizontal. So let's have that force that is applied, right? So we have FA, A denoting applied. And then no questions asked. Any object on Earth will always experience FG, right? The force of gravity. So we have Fg. And then if that body rests on a surface, then the surface will exert a normal force on the body, right? So there we go, normal force. And then apart from the normal force, the 2 kg and the 5 kg block are connected by a string, right? So we must have tension, right? So we have tension there. We are also told that there's a kinetic frictional force acting on the blocks, right? So we can have Fr also acting to the left. So let's, do 2.1.3, which says that let's calculate the magnitude of force F. Force F is the applied force, right? That must be applied at an angle of 20 degrees to the horizontal to make the 2 blocks accelerate at 2 meters per second to the right. So in this situation, we need the acceleration to be equals to 2 meters per second. So here, we're trying to find the magnitude of force F that must be applied at an angle 20 degrees to the horizontal, right? So the force F that is applied, it's applied on the 5 kg block. So we're going to go to the 5 kg block and try see if we can get the magnitude of force F. So what are we essentially saying? We're saying that for the 5 kg block, right, F net is equals to ma, right? So now in place of F net, we can add the forces that are acting, and in place of ma, we have the mass and we know the acceleration. So which forces are acting? We know that along the horizontal, we are going to have Fa x, right? We're going to resolve the force applied along the x, right? And then now we're going to minus all the forces that are opposing the motion. Which forces are opposing the motion? Obviously, frictional force will be opposing the motion, and then the tension force will also be opposing the motion. And this will all be equals to ma. So what is Fax? Fax will be the force applied multiplied by cos of 20 degrees. We know fully well that if you want to find the x component, you take cos of the angle, and then if you want to find the y component, you take sine of the angle, assuming that you are on a flat surface, right? And then minus frictional force. The frictional force, it is said to be equals to 15 Newton, right? So minus 15 and then minus the tension. We don't know what the tension is, so we're just gonna leave it like that for the moment. And then that is all equals to ma, right? We know the mass fully well. The mass is 5, and the acceleration, we're assuming that it is 2, right? The equation says, let's find the magnitude of the force F that must be applied if the blocks will accelerate at 2 meters per second. So now, let's go ahead and solve for Fa cos of 20 degrees, right? So we have Fa cos of 20 degrees being equals to, so we're taking minus 15 to the right hand side and minus tension, right? But then on the right hand side, we have 5 multiplied by 2, which is just 10. So we're going to have 10 plus 15 plus tension, right? So now we can divide both sides by cos of 20. So we're going to get force applied being equals to 25 plus the tension divided by cos of 20. So it's easy to see now that we just need the tension. If we get the tension, then we basically have the force applied, right? So we have already used the 5 kg block. What we can do now is to use the 2 kg block and see if we can get the tension from the 2 kg block. So from the 2 kg block, there is the tension that is pulling it to the right and the frictional force that is pulling it to the left, right? So we're gonna have something of this manner. So we have 2 kg, and then in place of 2 kg, we know fully well that F net is always equals to MA. So now the force that is greater than the other is the tension, and then we're going to subtract the force that is opposing, which is the frictional force, and this will be equals to MA. But we know fully well what the frictional force is, right? It's given to us. It is said to be equals to 10 Newton, right? So we have frictional, which is 10 Newton. The mass is 2 kgs, the acceleration is 2. So the tension is basically equals to 4 plus 10, which is equals to 14 newtons, right? So here in place of T, we can substitute 14 newtons. So we're going to have 25 plus 14 divided by cos of 20 degrees. And if you put that in your calculator, you're going to get the force applied being equals to 41.50 newtons, right? And we basically done with that equation. Let's move to 2.2. 2.2 is saying to us the Earth exerts a force of 1842.5 newtons to keep a satellite of mass 200 kg in orbit around the Earth, as shown in the diagram below. We have a very fancy sketch there. And then the question says, let's calculate the distance above the Earth's surface at which the satellite orbits the Earth. So let's look at the information we have, right? We have the force that is acting between the Earth and the satellite. And then we have the mass of the satellite, right? Apart from the mass of the satellite, we have the mass of the Earth, because the mass of the Earth is a constant, right? So we have the mass of the Earth. And then now, what we're looking for is the distance between the Earth and the satellite, right? So we can use Newton's law of gravitational acceleration, right? Every body attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square distance between them, right? So we're saying that F is equals to G, that G being a constant, right? And then mass of the satellite, mass of the Earth, and then divided by the distance between them. The distance between them will be equals to the radius of the Earth plus the actual distance between the Earth and the satellite, right? So we're saying that F is given to us, right? 1842. So we have 1842.5 being equals to that capital letter G, right? Which is a constant. It's 6.67 times 10 to the minus 11. So now the mass of the satellite is said to be 200 kgs. And then the mass of the Earth, right? 5.98 times 10 to the minus 24 divided by the distance between them, right? So we have distance squared, right? So now we're solving for the distance squared. It's easy to see. We know fully well that if we have A is equals to B divided by X, and you want to find X, you want to cross multiply, right? You're going to get AX is equals to B multiplied by 1. So X will be equals to B divided by A, right? So we're going to apply the same idea in this situation. Our X is D squared, right? So we're going to have something like this. So we're going to have D squared being equals to this entire expression here, right? So let me just duplicate it for the sake of time, and then we dividing that by 1842.5. And then after you do that, you definitely take square roots on both sides, right? So you take a square root on this side, and then you take a square root on the right hand side too, and then you're gonna get a distance of 6,579,982.8 meters, right? So this is the distance between the Earth and our satellite. But then we don't want the distance between the Earth and the satellite. We want the distance above the Earth's surface at which the satellite orbits, right? Even if you look in the question here, it's in bold, right? The distance above the Earth's surface. So that distance will be equals to the distance we just calculated right now minus the radius of the Earth. This question has 5 marks, right? So if you stop here, you only have 3 marks. The other 2 marks is for you to subtract the Earth's radius from this value that we have. So if we do that, we can now say the distance above will be equals to 6,529,982.8 meters minus the radius of the Earth, right? The radius of the Earth is a constant, so we know fully well that that is 6.38 times 10 to the 6 meters, right? So your answer is going to be equals to 1.9998 times 10 to the 5 meters.